Okay, to do another example, to try another example, let's let capital D be the region bounded by y equals 9 and y equals x squared. And then let's find the double integral over d of 3x squared minus 2y dA. Okay, for an answer to this, let's go and draw a picture of the region that's being described. So it is between, capital D is the region between two shapes, right? Between the line, the horizontal line y equals 9, and the standard parabola y equals x squared. So there's the parabola, let's say, yeah, and then there's the line, and we're trying to talk about this shaded, and that's capital D here. Okay, and we know, I don't know if we're going to need it or not, let's just go ahead and label here on the x-axis the 3, on the y-axis the 9 there, and how about why not get the negative 3 in here, just in case we need it. Okay, so look, one option to do this, it's certainly an option, is just, you know, the double integral over d of 3x squared minus 2y dA is to literally set up an, you know, an iterated integral like we would have done in the previous section. So 3x squared minus 2y. Let's see, do we want to do a dx dy or do we want to do a dy dx? I'm thinking, based on the picture here, let me switch colors, that it'll make sense to, it'll be much easier to have a fixed value of, what is that, of y, and then see the upper and the lower, let's see, I don't know, actually that, yeah, it's either way looks just about as, oh yeah, then we don't have to solve, actually. Either way is fine, now that I think about it. But for a fixed value of x, let's do that. You've got the lower y value, which is given by the parabola. Oh yeah, no, that's, either way is actually relatively easy. But let's go ahead and, so for a fixed x, so then let's get dx on the outside, dy on the inside. Y goes from, not from 0, oh my goodness, it's not shaded down here. Y goes from the parabola, from x squared all the way up to 9. X goes from negative 3 to 3. Okay, so this integral can be computed. It's not bad. However, let's also, and we won't continue doing this integral. It's very fairly easy to do, right? There's nothing really strange about integrating things that are polynomials. There's no sines and cosines and whatever else, fractions or whatever. But just to provide a second option, let's take a look at the question we were asked and think about it as if it's the right side of Green's theorem and then turn it into the left side. We have not really done that, I think. So it'll be good to practice, you know, Green's theorem both ways, right? So either a single integral gets converted to a double integral or a double integral gets converted to a single integral. So in order to do that, let's write the problem a little more carefully. So double integral over d of, I'm going to leave a little bit of spacing here, so 3x squared minus 2y, kind of a lot of parentheses, a lot of space, dA. And this part here, that 3x squared, we'll have to treat that as a dq over dx. So partial derivative of q with respect to x, and then a minus sign there is the minus sign there. Okay, that's good. Minus sign is minus sign in formula. So then the 2y without the minus sign, that should be partial derivative of p with respect to y. I'm just trying to match up the pieces in the theorem as we had it. So then that's going to equal the integral over c of, and then we'll see here p dx. So p dx, well, take a look. The derivative of p with respect to y is 2y. So then p itself should be y squared. Right? So this here needs to be capital P, because if all we're doing is integrating 2y with respect to y. Because the thing is, this, I assure you, this is what p needs to be, because we're supposed to have, if that's p, if p is y squared, when you differentiate that with respect to y, with respect to y, excuse me, you get that 2y that's right there. Okay, and then we'll write down the dx that's here. Plus, we have q dy. So let's see, if this 3x squared is what you get after differentiating q, which we're going to write here, yeah, with respect to x, then it should be clear that q has to be x cubed. right? So if q is x cubed, then differentiating x cubed with respect to x would give 3x squared. Okay, dy, as we see in the Green's theorem formula up there. Okay, so again, I hope that made sense of how we got the y squared and the x cubed. We were doing, I guess, partial integration. And then what's c? Well, c is supposed to bound this shaded region over here. So if we were to draw maybe c, capital C on its own, so what is this c? It's, if we were to draw a picture, it's really, maybe I'll use a new color to draw capital C. It's that parabola, and then a straight line across, traveling counterclockwise, of course, because that's what Green's theorem asked for. The way to think of this, though, so C is this curve, and C is counterclockwise, but it really makes sense to break up C into two separate pieces. So how about the parabola piece, which we'll call C sub 1, and then the line segment piece, which we'll call C sub 2. So let's go ahead and parameterize, okay, that C sub 1, a way to parameterize this, we'll do this, just highlight this in another color, in blue as well. Okay, to parameterize this, I think the easiest option is just to say, how about x is just t, right? So x is equal to t, and then y will be, well, if y is x squared, then now y is t squared. And t here would go between negative 3 and 3. Okay, so there's a parameterization of c sub 1. And then c sub 2, parameterization for that, it's just a line segment from 3, 9 to, sorry, there's not much room here, negative 3, 9. So isn't this just x is equal to, starts at 3, change in x is negative 6. So minus 6t. Y is just a constant, is 9 the whole time. And t goes between, well, 0 and 1 for parameterizing a line segment. Okay, so we've got a parameterization of C1, we have a parameterization of C2. And then, if all we're supposed to do now is this integral over, so it says over C, but we're just going to break up C into the two separate parts, so C1 and C2. So it's really two separate integrals, right? So we've got this here ends up being equal to an integral. Let's do the integral over C1 first. So t values negative 3 to 3. And then we're supposed to have y squared, but y is t squared. So how about t squared for y, and then squared because of the square that's on that. Then dx, so that's, well, we need x prime. So when you differentiate t, you get 1. And then we could stick the dt here, but let's just, there's going to be the other part for the y, so let's just work that out. So there's the x cubed, so plus x is t, so t cubed, and then dy, so we need the derivative of t squared, which will be 2t. Okay, let's just move this a little closer. Plus, and then we need an integral over c sub 2. So now just think of this as a different t. I mean, this t is unrelated to this t. If you just want, the t's that appear here could just be s's or something. But we'll integrate t from 0 to 1. And, okay, y squared. So that will, in this example, be 9 for y and then squared. Dx, though, is going to be differentiate 3 minus 6t, so you get negative 6. And then there should be a dt right here, but there's going to be another dt anyway, so we'll just, in a sense, factor out the dt. Then we have x cubed. Okay, so we've got 3 minus 6t is x cubed. And then dy is supposed to be the derivative of y. So the derivative of 9, that's a 0, times a dt, but there's that dt that we had factored out. So here's the integral that was due to C1. This is the integral that was due to C2. And let's just say we're done. Both of these integrals here can also be done, just like the integral up here can be done. Now it should turn out that both this, we have not used green recently. Yeah, sure. So this right there, if you go through with that integral, it shouldn't be bad. It's something that you could do back in the last chapter. And then if you did this, now it looks a little tedious, but you could give this to a friend taking Calc 1. Either option should give you the same answer. And what should it be? So either way, the integral should be negative 972 over 5. So the whole point, I think, this time around was just to say you can use Green's theorem backwards as well. Okay, and so I think the point is to say, look, there's this integral up here, there's this right here, and maybe not every time Green's theorem is the right thing to do, right? Because Green's theorem in this example just turned it into a mess. And how can you know for sure? You never really can, right? That's somehow just like how integrals themselves, you had to be very strategic. You kind of just need to set up things and either attack the integral you have or go, ooh, maybe what I have is tedious, and you're going to switch it around. Maybe the question we were asked would have you naturally set up this instead, and so then by Green's theorem you get that. So you have to kind of write things out with these theorems and see what you get. So just to try to put some words to this, it's not that option 2, and by option 2 I mean the option that's not direct, right? The one that uses the theorem. It's not that this is always easier. It just depends on the problem. Okay, it's not that option 2 is always easier, but in principle, Green's theorem can be used backwards. Okay, so yeah, backwards, from a thing that looks like this to a thing that looks like that. And in some cases that's nice, and in some cases it's not as nice. But just we did it here to demonstrate that you can. Let's also, even though you can, let's just make the comment that we won't typically use Green's theorem backwards so often. So we won't use Green's backwards so often. But I still encourage you to practice, to think strategically as much as possible, because there is a variant of Green's theorem that we're going to look at where we will use it backwards. But we will use a theorem called Stokes' theorem. Coming up later, we will use this backwards. Quite a bit, actually. So the Stokes' theorem business, that's going to be in about 2 weeks from now. But that's the whole, the whole point here is Green's theorem allows you to convert a single integral into a double integral, or a double integral into a single integral, as long as the single integral is over a closed curve. So just, why not just use the opportunity now to practice? Let's go ahead and do another example, and let me just clear the screen a little bit first. All right, so let's use Green's theorem to find the integral over c of xy dx, where capital C is the following shape. So we'll draw. It's most of a unit circle, actually. So there's this line segment, and we'll travel this way. So from the origin out to root 2 over 2, comma root 2 over 2. Then you travel along a unit circle. And then you end up right here. Stop at root 2 over 2, comma negative root 2 over 2. And we've traveled counterclockwise. We'll draw in a couple arrows to indicate that. And then from this point where we've just stopped, travel right back to the origin along a straight line. Sorry, my picture of a straight line isn't all the best. That's because of the app I'm using, so apologies. Okay. As an answer to this question, so the integral over this curve, x, y, dx, is equal to, well, let's make it look like what we have right here. So let's have this become integral. We've got to make some choices, unfortunately. Well, I guess the choices are not so bad here. So x, y, and then there's a dx part. So this dx is that dx, and then you might say, well, where's the dy part? Let's just tack on a plus 0 dy. Okay, integrating 0 doesn't change the value, right? So our p in this example, p is xy, and then the 0 right here is capital Q. Okay, then by applying Green's theorem, this is going to get converted into a double integral. We'll talk about what the region D is in just a moment. But you've got dq over dx. So the derivative of q, well, if you differentiate 0 right here with respect to x, you're just going to get 0 anyway. So let's just point out, though, that just being very literal, that this is the partial derivative of q with respect to x. Then there's a minus sign in Green's theorem, so let's copy down that minus sign. And then we have dp over dy. So we should differentiate p in this example is xy, so we need to differentiate xy with respect to y, and we'll get x when we do that. Okay, so let's just, maybe notate here. So the minus sign was copied from Green's theorem, but then the x is the result of partial derivative of p with respect to y. And let's copy the dA that's right here. Now, let's take a moment to talk about what this capital D is. So if C is this shape right here, we travel along this way, counterclockwise all along, then what is capital D? What's the region that it bounds? Do you have a name for this thing? What is capital D? It should be not the best picture. Forgive me. This is part of drawing on a screen. But this is Pac-Man, right? This is a unit Pac-Man. Unit Pac-Man. Unit because radius 1, of course. Unit Pac-Man. Okay, so then if we were to set up, look, this integral right here, I don't really want to write an integral as a dx dy or a dy dx. I think based on the shape, the right thing to do is switch to polar coordinates, right? So switch to polar coordinates. It'll just make it an easier integral. We've got integral sign. Let's just leave a little bit of space. What we're integrating is negative x, so that becomes negative r cosine theta. And then, I meant to leave a little bit of space. So negative r cosine theta. Okay, so that's what negative x became. And then dA, of course, becomes r dr d theta. R dr d theta. dr is in the middle, so r, well, it's unit, okay? It goes from 0 to 1. And then theta goes from, well, take a look at the angle here. Pi over 4 all the way up to, not all the way up to 2 pi. So pi over 4 away from 2 pi. So I believe this should be pi over 4 all the way up to 7 pi over 4. Okay, we won't actually compute this integral. There are some details. It's really not that bad, so you should give it a try yourself. But you should end up getting root 2 over 3 for it. Now, this is, I think, a good time to have an interactive question. And we'll say this. So I'd like you to outline the work. Outline the work involved if computing the integral of f of x comma y equals xy over the curve C, outlining Pac-Man with respect to dx, okay, a dx integral, if Green's theorem is not used. I mean, what would you have to do if you had to do this directly? Now, you don't have to do the actual work, so let me clarify. You do not need to. I mean, you can if you want, but you do not need to do any of the computations The idea is you should outline. In other words, you should outline the recipe. So it doesn't need to be overly detailed, but I'm just saying you should, tell somebody kind of the general steps they need to do. So step one, do this, and then do this, and then do that. So don't go through the computations, describe the computations. I just want you to see kind of how long the list is, that's all.